I'm here to talk to you about the age of data and AI, which I'm going to say is now. I'm going to tell you a story of sorts, a sort of a narration through that process. And well, I guess let's start with my story real quick. I'm Derek, technical lead at IBM, the HyperBlue Fund. It's sort of an intramural startup program that we have. And yeah, so some of you may have sniffed this out already, or maybe I told you directly, but I'm not actually a marketer. I'm a software developer. So I'm from down here from Massachusetts. I haven't been to DC in like a decade and a half, so it's kind of cool to be back here after so long, see how much has changed. I graduated with a degree in computer science and cognitive science, and since then I've been working at IBM on projects in and around the space of this Watson technology, right? In 2011, well, before 2011, we started ourselves this grand challenge, this research challenge, that we were going to play and win Jeopardy. And we did that in 2011. We won. I wasn't part of that team, but I was part of the team after that that sort of said, well, okay, this is really cool technology. This did something incredible that's never been done before. It had one user, though. That was Alex Trebek. And maybe we want to sort of figure out ways to generalize this so that it has more than one user, right? It's good technology. Let's let people use it. I'm a big fan of context, just as a premise for conversations. So I don't like sweet potatoes, and I apologize if I offend any sweet potato fans here. You've made an incorrect choice in my estimation, but fair enough. So just keep that in mind. It might be important, it might not. I don't know. Let's talk about a more interesting story, though, which is the age of data and AI. It's right now. We're living in a time of incredible amounts of AI. We're all customers of AI these days. We all use Google. That's the easy one, right? We all use Netflix, like the recommendation queue in Netflix, right? That's powered by artificial intelligence, predictive analytics, right? We're all indirect customers of AI too. AI is optimizing our power grids. It's forecasting our weather. It's helping our doctors read our X-rays. And then as we sort of tease too, like a lot of us are starting to get into the business of AI, right? Gartner says that 34% of organizations are using AI already in some way, shape, or form. For those of you who aren't, you must be then part of the 75% of organizations who are considering using AI in the near future. It's on track to be a $126 billion industry by 2025, which is like just around the corner, right? Time flies. So we're living in this time right now of AI, and I want to talk sort of about, again, context. I want to talk a little bit about how we got to where we are now, a little bit of the history. I want to talk about what's going on right now and what you can use AI for right now. And then I want to talk about sort of where we think it's going next, what some of the things on the horizon are, and maybe how you can get on top of them as they're happening. But yeah, we're going to start with the story of AI, and most good stories start at the beginning. So shall we? Sometime in history, Talos was a bronze Titan statue that guarded the island of Crete. This might be mythological, maybe true. I don't know. We weren't there. Well, that's the beginning, but let's skip ahead a little bit further to 1770, the Mechanical Turk, a chess-playing automaton. Well, it wasn't really an automaton. You can see from the little door there that there's a guy inside who knew how to play chess really well. And so when people came and played the thing, they thought the machine was winning, and it was just another guy. Incidentally, if you're familiar with Amazon's Mechanical Turk service, that's where the name for this comes from, or name for that comes from this. Automaton, again, Greek for the thing that moves itself. You're going to hear that term a lot in artificial intelligence. That's an interesting start. It's one of the first sort of hype cycles around AI and the smoke and mirrors that you often see. But let's skip ahead a little bit further. 1950, this is Alan Turing, the man who cracked the Enigma code, the secret communication system that German submarines used to talk to home base during the Second World War. You may have seen the movie about that called The Imitation Game. The Imitation Game, incidentally, was not about the program to crack the Enigma code. It was about something else. We call it the Turing test right now. And it's a metric, a test, an evaluation to figure out whether or not the thing that you're dealing with is fully artificially intelligent or whether it's just sort of imitating the imitation game, right? It's an interesting start. Alan Turing is really important, but I think we're going to skip ahead just a little bit further to 1956. And this is the Dartmouth Summer Conference on Artificial Intelligence. It was organized by a guy called John McCarthy, not related to the other John McCarthy. And he was kind of a big deal in math at the time. And he was going to become a big deal in this field of artificial intelligence. That's him right there. And he didn't really invent artificial intelligence. It's not the beginning of the thing, as that little fast forwarding through history we just did might indicate. But the beginning we're talking about here is a beginning of vocabulary, right? The term artificial intelligence was coined at this conference. And it was sort of this bringing together of all these big minds at the time, people who had sort of lived through the invention of the electronic computer in the 30s and 40s. That's the electronic computer essential to Alan Turing as well, cracking that Enigma code, the bomb, as it was called, in Bletchley Park over in England. But yeah, so a bunch of guys have been thinking about this and formulating their own ideas and formulating their own models for what artificial intelligence was. And they have their own names for it, right? Automata theory, that term again. Complex information theory. Can't believe that one didn't catch on. It's super memorable. And this was sort of an effort to bring them all into line and get them all thinking together. And a lot of these faces sort of became big names in artificial intelligence afterwards. And maybe you might have heard some of their names in headlines or in a history textbook or something. Marvin Minsky was there, right? The professor from MIT. Claude Shannon, the inventor of information theory. Oliver Selfridge, Nathan Rochester, an IBMer. All these big names, these big heads coming together in this convergence moment for the field, the official start. And they even had a pitch for it. This is their memo that they used to pitch this conference. I love this memo. It was super optimistic, as you can see. We propose that in a 2-month, 10-man study of 1956, 10-man, of course, study of artificial intelligence, we believe that significant progress, significant advance can be made in one or more of these problems of artificial intelligence. I love the optimism. I've written memos like this myself. It encapsulates this brain problem, I think, that people have, when smart people have when they think about AI and they look at it and they go like, well, look, I got a brain. I know how to think. How hard could it be? How hard could it be to crack this? Well, it's been 70 years and slightly more than 10 people have attempted to crack it. And you know what? Fair enough. Significant progress, significant advances have been made in the field. I mean, we've come a long way since that summer conference. We've come through the 60s in the age of what we call symbolic AI, right? This rule-based system. I don't know, anybody remember doing like trigonometry proofs in grade school where you had to write a bunch of rules and that's sort of how you demonstrate that this statement is true? It's basically what symbolic AI is, except it's just a program that runs it instead of you executing the logic and trying to pass things through it. And that was really cool. It did things that computers couldn't do before. It solved problems that people hadn't been able to solve up until then. And it had a lot of potential, and that potential was filled, and then it started to stop delivering. People got their hands on it, and they're like, all right, well, it worked for me for this case, but it's not that smart, really. I can't have a conversation with it. Like, what is it even doing, really? Like, yeah, maybe it works in this case, but in this case, give me a really bad answer. And so we enter the first of what we call AI winters in the 70s. And these AI winters are sort of doldrums of like hype and optimism. The hype was so high in the 60s. Like everybody's like, oh, AI. They told us 2 months, 10 men, we're going to crack it. And then they didn't. And okay, well, I'm kind of bored. Like, come back to me when you got something good. Funding dries up, optimism dries up, hype dries up. Thank goodness for the government keeping academic research alive throughout that time, because that's sort of the lifeline of university research that was continuing to sort of move AI forward through this public lack of enthusiasm for the thing. And that lets us emerge out sort of the other side of this first AI winter. And yeah, spoilers, as you can see here, there's more than one. This cycle is indeed a cycle. It keeps happening. Out the other side into what we call expert systems. And this is sort of in the early 80s. This is a big deal. There's sort of extensions on the symbolic logic that you see earlier on. They're bigger, they're more flexible, they're more powerful, they're a little smarter. And people start to get excited again, right? They look at it and they go like, wow, okay, I remember the 60s. The technology then, whatever, like it was cool, it did some things, but this thing is kind of cooler, it's kind of smarter. Maybe it's even smarter than I think. Maybe we're starting to get there. Maybe we cracked it this time. We didn't, of course, right? And so the exact same process happens again, right? We go through this second AI winter, the second big AI winter. There's actually more than two, but we're going to focus on the two big ones. The second, doldrums of enthusiasm and optimism, and of course funding and government funding keeps research going on the process until the public sort of starts to get excited again. And that happens in the 2000s, technically the early 90s, into the 2000s, with the rise, the resurgence really, of machine learning, because it's not just the hype cycle that's sort of cyclical in AI, it's also the technology and thought process cycle as well. So machine learning represents kind of a sea change, a paradigm shift in how AI is built. The old AI, the stuff we've talked about already, is what we call now good old-fashioned AI, GoFi, you might see it called. There's a famous incident where in 2013, we'll talk about it in a second, somebody gets up on stage and basically says, GoFi is dead. We are in the age of machine learning. Machine learning and GoFi differ in the sense that with good old-fashioned AI, you've got a subject matter expert, somebody who knows the domain really well. If you're trying to build an AI that does language, right, you bring in your linguists, and they think about the problem, and they're like, oh, I've studied this problem before. I've got ways of breaking it down. I'm going to try and write down a bunch of rules, a bunch of logic that models this problem. I'm going to build the model myself by hand, and you need subject matter experts to do that. There's a problem with that. Not every subject matter expert has the same opinion about how the right way to go about solving the problem is. And on top of that, some of them might even be wrong. They might have incomplete representations of the problem in their head. They might not actually know it as well as they think they do. And so the AI is only as good as the subject matter expert that's building it. And what machine learning says is, all right, that's cool. These models are powerful. They did some things, but let's see if we can cut the human out of the loop for this process of actually building our AI, for creating something that understands, right? Can we build a system that instead of like built by hand and then answers the problem, answers the question, can we build a system that builds a system? Can we build a system that knows how to learn, knows how to train itself? Can I build a system that uses statistics? And this is the big sea change shift from logic and model-based good old-fashioned AI to statistic-based machine learning. Can I build a system that if I throw training examples at it, if I throw just a bunch of data at it, it can find the commonalities that a human might be doing in their process of learning how to model a domain. It can find those same commonalities, find those same associations, find the rules. It's still writing rules, but this time the statistics are writing the rules, not a person anymore. And in theory, what that means is that we can get a little bit closer to maybe not the truth, but something that's freed from the biases that a given person might bring to the process. Cyclical, like I said earlier, machine learning, not new in the 2000s. It was in fact invented, well, canonized, let's say. It was invented a little earlier in the 50s. Marvin Minsky published a book in the 60s called The Perceptron, which sort of is like the start of machine learning. But computers weren't powerful enough back then to actually do anything with it. So, it sort of had to wait for its time, and its time was there. And that brings us into the age that we find ourselves in right now, which is the age of deep learning. And there's a specific timestamp where you can point to that starts it, and it's 2013. And it's a paper published by a guy called Jeff Hinton, who works at Google now. This is incidentally the guy who got up on stage and said, GoFi is dead. He's very proud of himself. And rightly so. It's an accomplishment. Deep learning is machine learning on steroids. It's machine learning that cuts even more of the requirement for human beings to be involved in the process. It cuts even more of that out of the loop. Now, instead of having to sort of coax the data to fit into the machine learning algorithm, you just sort of like throw raw data at it, and the machine learning algorithms are smart enough to pick up on patterns that you used to have to model yourself. So it's the next step in machine learning. And we've been mining that vein of innovation ever since, right? I mean, some of you have probably seen some of these headlines recently, or maybe even had a chance to like play with some of this stuff. I mean, I think of GPT-3 out of OpenAI, right? This big open-ended language model, huge, like trillions of examples, petabytes upon petabytes of data that go into this thing and are used to represent this thing. You couldn't run it on your computer; it's just too big; it wouldn't fit. And it's what we call a generative model. It takes a little bit of a prompt, you seed it with something, and then it tries to predict what's going to happen next. And that's a pretty open-ended way of framing a problem, right? What's going to happen next could be, oh, well, I seed it with a question, and it tries to predict what's going to happen next, which is usually an answer in its experience. So it's a question-answering system now. I can do weird things with it. It's read enough websites in its examples that I can seed it with a description of a web page, and it'll output the HTML and CSS to make that web page happen. I say, give me a web page with a button that says click me, and it does it. It gives me the code, it runs. It's not good code, it's not pretty, sometimes it doesn't work very well, but it does it. There's been some more recent ones too. Maybe you've seen DALL-E out of OpenAI as well, or Imogen out of Google, sort of competing in the same space, this new space of like multimodal models, multiple modalities of sense data, right? It's not just dealing with text anymore. It's translating in between text and images. You give it a description of a picture and it gives you the picture. I can go to DALL-E and say, give me a picture of a dog wearing a hat in the style of Picasso. And it'll give me that. Sometimes they're pretty good. Sometimes they're really not very good, and it's pretty funny. I wish I had some examples to show you, actually, because they do get pretty funny. But sometimes it's uncanny how good it is. And that's, of course, the examples they cherry pick for their publications. It's like, look at this, look at what it does. And then they have a little disclaimer at the bottom that says, like, there were a lot of other runs that didn't look this good. But sometimes it does work that well. And that's cool. That's exciting, right? We don't necessarily know how that's going to play out yet. It's still in this sort of early research phase, but the potential is there, and it's all based off of this deep learning revolution. So, these models are getting bigger and bigger and bigger, and every step of the way they've been driven by the increase of data in the world, right? The data is the fuel for machine learning. It's the raw material, it's the fertilizer. You need data to build these models, to give them more examples, to find the nuance, find where the rule splits, right? Find where the decision tree changes, and it needs to make a different choice. And at the same time, with the growth of all of this data in the world, we need AI to parse through it all. I mean, like, just for example, every second, 3 million emails are sent. 60,000 Facebook posts, right? 6,000 tweets, a full hour of content on YouTube every second. That's way more than human beings can sort of annotate and process now. And so we need AI to start keeping up with it all, right? And that AI has to be able to grow and adapt and change. Oh, I should have skipped that. Grow and adapt and change and keep up with the rate of the world underneath it. I mean, the shape of this data is changing all the time. The underlying substrate of your data changing all of the time. What was we sort of heard about this yesterday, right? What was a hot topic yesterday might not be a hot topic tomorrow, right? You may have missed the opportunity to capitalize on it if your models are moving slowly. And what even something as foundational as the substrate that we're all talking to each other on, the language itself is changing every day, right? The youths might have introduced a new piece of vocabulary into the domain, right? A new bit of jargon and a new cool way of phrasing things. And if your model's not up to date on that, then it's not going to understand the language itself anymore, and everything starts falling apart from there. So you need something that can keep up with how this data is changing and how the world is changing around it. It needs to be able to move fast. It needs to be able to adapt quickly, and it needs to scale because of how much data there is. And so what does that mean for us in the business of artificial intelligence, whether you're using it now or whether you want to use it? Well, it's tricky because, like, it's cool to see all this cutting edge stuff. We want to use this cutting edge stuff. The cutting edge stuff isn't really ready for us yet. But there's a lot of things that are. There's a concept in the domain that I like a lot. It's called the vanishing problem of AI. And it's kind of a joke, and it's kind of a truth in the way that you sort of half joke and half truth. But it says that as soon as we figure out how to do something with AI, there's a hard problem. There's something that we didn't know how to do before with computers, and we've been working at it. Some people maybe even start thinking, oh, maybe it couldn't be solved by computers. Maybe it's something that only the brain can do. And then somebody does solve it. Somebody makes that little bit of progress, right? That advance happens. The timeline might be longer than expected or promised, right? But it does happen. And we solve it, and people stop talking about the problem with that same sense of mysticism that you hear when you say AI, right? It's no longer AI. It's just something we can do now. It's something that everybody can sort of get their hands on and make something with. It's not hard anymore. And a lot of the things that we've made progress on, the things that have vanished into just things we can do, are the kinds of things that let us bridge the gap between technology and people. And what I mean by that is, let's see. So do you remember what it was like to use Google in the early days? Like the start of search engines, right? Alta Vista, even if you want to go back that far, or Yahoo. You were writing database queries, right? You had to like wrap it in quotes and like put a plus, just like I have to include this term, or put them. You couldn't just address the system like a person. You had to meet it where it was. You had to change your mindset, change how you thought, change how you were phrasing your question to meet the system where it was and accommodate for its limitations, because it wasn't smart enough. Compare that to now, right? Like if you try and put like just keywords into Google, it does a worse job than if you put an actual full natural language sentence into it, right? So, you know, the problem of like, all right, well, how do I take what a computer understands and have it extend to what a human understands? Those problems have started to be bridged. And what it's letting us do now is start to hear the humanity behind this sort of like raw data that we're dealing with, right? We're not just looking at numbers when we look at data coming in, like those numbers were generated by something. They come from people at the end. And what AI lets us do is parse some of that, understand some of that, not just from the raw metrics perspective, but understand, you know, who's behind it, what they're actually trying to say to us, right? We can start interacting like humans through each other, right? And it lets us get at the voice of the user a little bit better. It lets us hear. It lets us pay attention, as we sort of heard yesterday, right? We can keep our finger on the pulse. We just have to know how to use the right tools. So what are the tools that we have? What's in the AI toolbox right now? Well, let's see. There are classifiers. There are linear regression algorithms. There are k-nearest neighbor algorithms. There are decision trees. There are neural networks, simple neural networks, I should say, convolutional neural networks. There are deep learning neural networks. There are recurrent neural networks. There are adversarial neural networks. There are LSTM neural networks. There are autoencoder. There's a lot of neural networks. Okay, there's a lot of algorithms out there, and they all have their own sort of stats, right? They all have different strengths and different weaknesses. You know, some of them are great for natural language processing. Some of them not so great for natural language processing, but awesome for image processing. Some of them, you know, they got a killer vertical and they just can dunk like nothing else, but they can't sink a three-pointer for their life. And that's not going to play in modern basketball or machine learning for that matter. What I mean to say is that there's a lot of algorithms out there. If they issued trading cards, I would collect them. Don't steal that idea, actually. I want to see if I can find funding for that. But the cool part is that they're commodity items at this point. They're part of the broader open source community. I can grab, you know, okay, well, I should say not all of them, right? Some of them, ones you talked about earlier, maybe the secret sauce behind DALL-E or Imagen is still sort of locked in a vault under San Francisco Bay, guarded by one guard who cannot tell a lie and one guard who can only tell the truth. But by and large, you've got access to these systems. If you've got a problem and you want to start building a solution, you can, right? So let's look at a problem. I've spoiled it a little bit by putting the thing that we're going to look at up there. Let's say I'm running a marketing campaign, and I've got all sorts of ways of calculating engagement with it, right? Of figuring out what people are thinking about my company afterwards. A lot of those are based around, you know, metrics like clicks and numbers of tweets and numbers of posts and all of that, hashtags, right? Whatever. I want to go a little bit deeper, though. I want to actually start to hear that human voice, hear what people are saying. So I want to use, I know I've got a lot of data floating around from Twitter. And I want to understand not just how much of it there is, but what it's saying. I want to do some sentiment analysis on it. I want to figure out if the tweets are saying good things or bad things. And that'll sort of help. That'll be another metric for me, right? That'll be another way that I can sort of look at the outcome of what I'm doing. So cool, right? Open source algorithms everywhere. I just need to grab one of them and I can get going, right? So, you know, I'm a Python software developer. Spoiler, we're talking about software at this point, right? Say I'm a Python software developer, right? I can just grab NumPy, it's called, which is a library of AI algorithms, and I can hook it up to Twitter, right? And boom, I'm done. I'm off to the races, right? Sentiment is coming out. Look, I can see the results, positive or negative. Ooh, I missed one. I always forget how many there are. There we go. Well, it's not that simple, because like we talked about earlier, this is not, you know, it's helping you understand what humans are saying, what the people are saying behind it, but it's not quite there from this level. These are just statistical algorithms, right? They're just math, right? They take in numbers, they do some stuff to them, and they put numbers out the other side. But we don't have math. We have tweets. We have, you know, recordings from call centers, right? We have Facebook posts. We have emails. We have human data. And in order to get it to fit into this algorithm, to fit into this sentiment analysis thing that we want to do, I have to do a lot of work. I have to adjust it and tweak it and coax it and force it and translate it, really. I have to translate it into numbers. And then it goes through the algorithm, and then it comes back on the other side as more numbers, which means that I need to translate it back out of numbers before I can sort of come to grips with it again as a human concept. And, oh yeah, so this was supposed to be that. He's looking at those metrics. So what I'm talking about with that process is we call them processing pipelines, usually on either side of these algorithms, doing that translation, sort of that coaxing of data and the translation back out the other side. But what I'm really talking about at this point is engineering effort, right? That's work. That's hard work. That's non-trivial stuff. That takes months to really get this answer right, to really build something that's going to translate this correctly. We've got reports indicating like $30,000 for just a proof of concept for something as simple as that sentiment analysis problem, and months of time. There's the rule in software development that I like called Boyd's Law. It's in reference to Colonel John Boyd, and it says that speed of iteration beats quality of iteration every time. Now, granted, he was talking about fighter jets in dogfights, but I did just see that new Top Gun movie, and therefore I'm an expert on that now, and I do think that the analogy holds. Right? Speed of iteration beats quality of iteration. You don't necessarily know what the future is going to be. You start making assumptions. If you start trying to plan out too far ahead, well, okay, what if you're wrong? Or even worse, like what if everything changes underneath you, and by the time your assumptions would have played out, maybe they were right if things had stayed the course you predicted, but they don't. So, how do we capture that speed of iteration? How do we make ourselves go faster? Because we can't just make ourselves go faster, right? It's not just a matter of like, oh, well, just exhort the troops, right? Like crack the whip, right? You can't just make yourself go faster. You have to have a tool. You have to have a system that lets you go faster. Right? You could say, I'm going to cut you a $2 million check right now if you go outside and run 70 miles an hour. I would love that check, but I cannot do that. My legs do not move that fast. I need a tool. I need something that's going to actually make me, in this case, literally go faster. I need a car, right? Or a bike, maybe, if you're really good on the bike. Lance Armstrong, perhaps, but not me. So we need these tools. What's been going on that front in artificial intelligence? Oh yeah, these are all the tools we have. They're framed from the wrong perspective for what we actually want. They're not solutions. Like if I have a toolbox, I don't have a house in that toolbox. I've got a bunch of stuff. I've got hammers and wrenches and nails and screwdrivers and saws, right? But there's no house in there. If I want a house, I have to build it, right? And so how do I build it faster? How do I get to that house faster? Well, let's talk about platforms and nouns. And this is sort of where we are right now. What I was just talking about, sort of the lead up to where the sort of modern age of data and AI, here's the now. Platforms and nouns, right? AI as a service has grown alongside software as a service. A bit of a time lag there. We started with software as a service, and then AI as a service sort of followed it. And all of the sort of the big software as a service companies, they offer these catalogs of AI solutions, prefabricated, right? They've done that processing pipeline work for you, that engineering work for you. They've figured out what the right sort of coaxing of the data is, and they sort of wrap that all together, and they put the algorithm in the middle, and they bundle it up, and they sell it to you under a name. Sentiment analysis, right? A name, a noun, a handle that you can use to get a grip on what this thing is for, what it does. So let's look at our little example earlier, because it's even easier now. We've got our tweets. I don't even have to build anything now, right? I can just hook Twitter up to my sentiment analysis algorithm, my sentiment analysis service, I should say. Hook it up, and I've got sentiment coming out. Cool. Perfect. Oh, too far. There we go. Perfect. So that's cool. That's a little toy problem that we just solved really quick with AI platforms. But we're not just in the interest of like toy problems, right? For complex analytics, to start really getting into the depth of what we need to answer a business problem with an AI solution, right? We might need something a little more than just sentiment analysis. Let's expand it a little bit. Let's complicate the problem, right? Let's say that I don't just need to do sentiment analysis. I want to build a workflow. I want to start with sentiment analysis still, right? I'm still interested in measuring the impact of my marketing campaign, but I want stuff to happen downstream based on what the result of that sentiment analysis was. Sentiment analysis outputs something, and I want to use that output to make a decision. And say if the sentiment is negative, I want to then go down to I don't know, let's say entity extraction, right? I can read the tweets, I can pull keywords out of those tweets, interesting keywords, right? Maybe they have to do with why people are unhappy in the first place, right? I can feed those then into a search engine, for example, right? I can get web pages based on those search results, right? I can sort of see what the broader context again of why people are complaining is, because I've just got search results back. I can parse those search results and pull more keywords out of that, or do a summarization of it so I can digest it more easily. There are all sorts of AI subunit solutions that I want to use in the system to build this workflow. And if it's positive, maybe I want to do something else. Maybe I don't know, I hook it up to Slack and I have it send a direct message to the CEO and say, hey, sales team, doing a great job. Look at all this positive feedback. So that's cool. We can do this. We can hook these things up, right? These services, we can instantiate them all. We can connect them together. But the trick is that while these services might be very good at understanding their own domain at this point, because they come packaged with their processing pipeline, they're not necessarily good at talking to each other. They have these nouns, they have these ideas that we can use to get a hold of what they're doing, what their inputs are, what their outputs are. They're comprehensible to people, but I might not be able to connect them like this easily. I might have to do some more data munging, right? Some more adjustment of the shape of the data. I might have to, honestly, we're back to engineering work at this point. It's the processing pipeline again, right? I've just pushed it up a level. I'm back to having to spend time with my engineers, if I have them, right? If I have a data science team even, in order to make something like this happen, because I have to write code to connect all this stuff. And let's say I do have access to that, right? Let's say I do have a team of data scientists, or I'm the world's greatest hacker and I can do it all myself, right? Even then, you're still talking about time. You're still talking about speed of iteration. You're still talking about the need to keep up with what the pulse is right now so you can react, but possibly not the ability to with these tools, right? So say we sort of decide on our problem definition and we start building it. And it takes us 2 weeks now instead of months, right? It's easier, it's a little cheaper, a lot cheaper, really. And it takes us 2 weeks to build it. Cool, we built it, we can try it out now. It doesn't work. We missed something, one of our assumptions was wrong, the data changed under us, I don't know. Maybe the order was wrong. Maybe I needed another AI component in there. Maybe the output from one wasn't clean enough to go as the input to another. And so I need to go back and fix it. I go back to my data science team, my engineering team, my IT people, whoever's building this thing for me, right? Or me, as the case may be, and some late nights ahead, and I start fixing it. And that's another 2 weeks. Great. This time, 2 takes, we got it. It works. Works great. But the world has moved on. It's been a month since we started trying to solve this problem, right? And our viable window sort of passed now. Right, maybe we kept some of the sort of historical data around, or we can use the Wayback Machine or something to sort of trawl the history of the internet and figure out what the effect was, but we don't have our finger on the pulse anymore. We can't react to it at this point. We can't move quickly. So we need something that's going to help us move a little more quickly, right? And that's where we think things are going. And so I want to talk about the power of composition. And I chose this picture for a reason, because in a compositional AI system, all the pieces are built to fit together. They're designed to know how to interact with each other, right? In addition to wrapping the, hang on there. In addition to wrapping the pre-processing pipelines now, or the processing pipelines, right? They also wrap enough context about what they do and what their outputs are and what inputs they can accept, what kind of data they need to do the work that they need to do, so that you can just sort of connect them together and they just work. Right, I chose this picture for a reason, because it's exactly like these generic brand nondescript construction blocks. You can only put them together in certain ways, right? You've got pegs on some and slots on others, and those fit together, but I couldn't put them side by side, right? The system dictates how I'm allowed to fit these pieces together. So I don't have to do the sort of engineering work of doing it myself, and I can still build gigantic things out of it, right? Structural integrity in gigantic things as well. It'll hold. You've seen some of those amazing things they have at Legoland, right? Those things are huge. I know they glue some of them, but that, we'll pretend they don't cheat like that. So yeah, what does composition give me as somebody who wants to use AI rather than somebody who's interested in I don't know, going for a PhD in AI? Well, it gives me flexibility, first of all, right? Because these things are composable, because they are designed to know how they should fit together, I don't have to put that work in myself, and I can just sort of try and combine them and experiment and play around, and the system's going to let me do that basically for free, right? I don't have to re-engineer it every time I want to change the order of things. It's flexible. It's also fast for the exact same reason, right? Instead now of having to build some code that connects these things, that code already lives in them. I just have to tell it what arrangement I want, and it does it. So it's back to Boyd's law, right? Now we have a thing that lets us go faster, right? We have a tool that lets us actually iterate. And then there's a couple other points that I think are interesting, and we sort of touched on them at the top too, from this perspective. They give me what we like to call transparency. Transparency, you might hear it sort of discussed in conversations around bias in artificial intelligence, right? Around just AI, around statistical analysis that sort of indicates that, like, all right, sure, yes, these models are learning to what the data says, but what if the data has bias? What if the data has skew in it? What if the data's wrong? The model's dumb in some sense. It's going to learn it anyway, and it'll start giving you answers that we don't want. Like, maybe they're quote unquote correct answers according to the data, but we as a society don't want those answers. We want something better. And the trick with deep learning, the trick with these sort of opaque statistical AI systems, is that they hide that whole process from you. There is no transparency. You can't see inside to what they're doing. You can look at the numbers. There are numbers flying around, right? But I don't know what those numbers mean. It's speaking a language that makes sense to it, but I don't know how to translate it. I can't translate it. My brain doesn't have the capacity to understand what all those numbers actually mean. So I just kind of have to trust it. I have to look at the output and go, well, I guess this is as good as it gets. In a compositional system, that's still true to some extent. The boxes that you're connecting, the subunits, like, they might have some opacity to them. You might not necessarily be able to see into exactly what sentiment analysis is doing. But the input and the output hooks on either side, those are ways to look into the system now, right? Because those are still that human parsable content that I can look at directly and understand. And I can say, oh, well, this input looked good. And I could look at that data. I saw what went in for this particular sort of transaction in the workflow. I can look at the data and I can say that input looked good. The output, that's weird. That's not what I want to see. And I can see how that polluted downstream. I can see that it changed the input and output of the next piece in my workflow, right? And so on and so forth, right? I get an audit trail. I get a paper trail. I can look at exactly what happened as data flowed through my system, and it's exposed to me in such a way that I can understand it. It's human readable data. So I think that's a really important sort of thing to harp on for this kind of era we find ourselves in with AI that's making more and more decisions that, you know, maybe need a little closer look before we let it go through and actually end up affecting the rest of the world. And then the last piece I want to sort of highlight with a compositional system is the extensibility of it. Say you do want to use Imagen or DALL-E or one of these big GPT models. Say you've got, I don't know, business analytics pipelines that you want to hook in. Say you've got a Rolodex of clients that you want to hook in, data sources from outside. You want to pull in Twitter. You want to pull in Facebook. You want to pull in a database that you have in your private sort of repository. You want to hook all these things in, and then you want outputs as well. You want to connect it to Slack so that it can tell you when things are happening, or ask you what the right thing to do in this case is, right? Maybe you want a human in the loop of the decision-making process. You can do all that with this system, with a compositional system, because as long as those other things that you want to pull in play by the rules, as long as they sort of declare themselves and say, hi, this is what I am, this is what I need to do my work, and this is what I give you on the other side, as long as they do that, the system is flexible enough to pull them in and say, great, I can connect you to things now. I know where you belong. And so that extensibility is key, because it means that this is not you don't have to sacrifice anything to start using a compositional system, right? You can just plug it into what you have already. Let's see. So yeah, let's go back to our example earlier. And the trick here is that I've been drawing these boxes and arrows, like we often do when we try and solve problems, right? We get to the whiteboard and we draw boxes and arrows. And then I've been saying, oh yeah, but it's not how it looks, right? Like, I have to go get software people to write this for me, or figure out how to do it myself. With a compositional system, this is the interface. This is what it looks like. I just drag and drop boxes. The software has already been written. It's smart enough to be able to link these things for me. And so I don't have to spend engineering time on this. I've gone from months when I'm using the direct toolbox approach down to, weeks when I'm using the platform approach, down to an afternoon, down to a couple minutes. I can prototype faster than I've ever been able to before. So what does it give me? Yeah, this is the picture of what I just said. Yeah. So it gives me this speed. It lets me iterate faster. It lets me get access to those human insights faster, and it lets me get to a solution faster, an AI powered solution rather than just the pieces that I would need to build one. So thank you. That was a lot. I know, a grand tour through history. I want to highlight something about the AI winters, just real quick before I wrap up, which is that the goal of all of this, the goal of this approach to AI is to try and mitigate some of those winters, try and control for it, right? Because we don't want this to seem like magic. Part of that opacity is that it's hiding the machinery of the thing from you, and it's a magic rock. It's like looking at your cell phone, right? I don't know what's going on in my cell phone. I just press buttons and things happen, and I have to trust that that output is what I wanted. But if I look at something that exposes its workings a little more, like say a mechanical watch, right? I can look at the gears and I can see how they spin and I can see how they talk to each other and I can understand a little better what this mechanism is doing. And that dispelling of magic is essential if we want to sort of keep AI going at a linear progress rate. And if we want people to be able to sort of get into it, right? I don't want you thinking that it's AI. I want you thinking that it's a thing that you can do. It's a thing that you can incorporate into your business right now. Better analytics, better understanding of the human voice, better ability to hear the user. And that's all I have. Thank you.